Hi everyone. Today in this video we are going to discuss about the concept of speed control of DC shunt motor. Why we need a speed control for DC motors? What or maybe the kind of application we need some control over the particular equipment or a machine, right? Similarly, if we concentrate or if we apply the DC shunt motor or DC series motor or DC compound motor in industry, the applications in industry may vary with respect to the speed, right? For example, if we drive a two wheeler or a car, if we are running at a speed of 60 kilometer per hour, then suddenly we are able to see a speed breaker over the road, then automatically we will control the speed and we will apply the brake of the two wheeler or a car, right? So suddenly the speed will be reduced, and after crossing the speed breaker we can raise the speed to catch the original speed, which is 60 kilometer per hour, right? Similarly, the same concept is applied for the speed control of DC shunt motor either in industrial applications or domestic applications, right? So basically there are two types of speed control available in DC shunt motor. They are, the first category is field current control method. There are two types of speed control method available for DC shunt motor. One is field control method and the second one is armature current control method or armature control method. These two methods can be also termed as field control method and armature control method. This can be also written as field current method and armature current method, right? Both are correct. And now with the help of expressions we can see how field control method and armature control method are employed for controlling the speed of DC shunt motor, right? So we know the relation for EB. So back EMF EB is equal to 5P NZ divided by 60A, where the changeable parameter or the fixed parameters of the motor are number of connector Z's and number of poles P and number of parallel path A and 60, right? The parameters can be expressed as PZ divided by 60A. These are all the parameters that cannot be varied by the customer, and the parameters that can be varied by the customer is, or the user is, phi Z, right? And this it is not phi Z, it is phi N, right? Phi N. So now this can be represented by a constant term, that is K. So PZ divided by 60A, can be represented by a constant term K. This K cannot be varied. These parameters are number of poles and number of connectors, number of parallel paths are fixed, that cannot be varied by the customer, and the term or the parameters that can be varied by the customer is or EB is equal to phi into N, or EB directly proportional to phi into N, right? Where phi is the flux and number of flux lines and N is the speed in RPM. So we can change the speed and flux. If we change the speed and flux, then simultaneously the value of back EMF is also changes, because both are directly proportional, right? We know the other relation, that is the voltage equation for a DC motor is V is equal to EB plus Ia into Ra, where this equation can be rewritten as EB is equal to V minus Ia Ra, right? Ia Ra. Now from this I'm going to write this expression EB direct proportional to phi into n can be written as phi direct proportional to EB divided by n, right? So from this expression, if the speed increases, then phi reduces. If phi increases, then speed reduces. Now I'm going to vary the field current of DC shunt motor. If I reduce the field current of DC shunt motor, then it will affect the number of flux produced in the DC shunt motor. So it will affect the flux. So flux phi will get reduced because both are field current and flux. Field current and flux both are directly proportional, right? So when I reduce the excitation current or field current, then the number of flux lines in the field winding will get reduced. So this will affect the speed. Now the speed will get increased, right? Now see this relation. I'm reducing the field current, which in turn reduces the flux, but speed increases with the help of this relation. So flux is inversely proportional to speed. Here I'm reducing the flux, so here the speed is increased. So this method can be used for above rated speed applications. That is 1500 RPM. Above 1500 RPM, we can control the speed using this method, that is field control method. This is field control method, field current control method, right? Now coming to this is armature control method. So we know that the value of voltage V is equal to EB plus IARA. This can be written as EB is equal to V minus IARA. Now I'm going to increase the value of IA. So if IA increases, then the total voltage drop of armature will get increases. So it will directly affect the back EMF, right? So if IA increases, I increase the IA, then IARA drop increases, which will directly affect the EB. So EB will get reduced, right? So if IA increases, then IARA value will get increases, which in turn EB will also get reduced, right? So this drop, I'm going to increase this drop. So when I subtracting this with V, then EB get reduces. Where we know that from this relation, EB is directly proportional to phi into n. Now I'm writing this as EB directly proportional to n. Now when EB decreases, then the speed will also get decreased. So finally, when if I increase the value of IA, then EB will get decreases, and which will directly affect the speed n, which will also get decreased. So this kind of method can be employed for below rated speed applications. That is 1500 RPM, less than 1500 RPM, and this is above 1500 RPM, greater than 1500 RPM, right? So this method and these relations are for field control method, and this relation is for armature control method. Here I am increasing. Here if I increase the value of field current, then phi will increase and speed will reduce. If I decrease the value of IF field current, then flux will reduce, which will indirectly proportional to speed, which is indirectly proportional to speed, so the speed will get increased. And here in armature control method, if I increase the value of Ia, then drop across armature resistance, armature winding will get increases, which will reduce the back EMF. If the back EMF is reduced, then it is directly affect the speed. So speed will also get reduced. So these are the two major type of speed control employed for DC shunt motor. Thank you.